Today I'm going to redo a talk that I gave at the Healthcare Information Management System Society Precision Medicine Conference in June 13th, in 2017, this year. The sound, we recorded that original presentation, but the sound had a little bit of problem, so I thought it would be good to redo that with a little bit better sound. And also, it gives me an opportunity to throw in some additional things that I think you'll find interesting. It is a rather long talk, so what we're providing here are the time codes for the different sections. So if you want to jump ahead, or if you're coming back to this video and you're looking for a section that you found interesting that you want to review again, you can use these time codes. Also, if you'd rather see the original talk from the HIMSS conference, you can see it, either go to our website and look in the news page. You'll see, if you look down through the press releases, you'll see the press release on HIMSS. You can click through and find the original video there, or you can just go to it directly at this URL. All right, so let's dive in and talk about the democratization of healthcare. So the idea behind the talk is what is going on with big data and precision medicine, and how is AGT related to that? What are we doing in terms of this whole movement of what they're calling precision medicine? So let's just go ahead and dive into it here, and let me explain a little bit about what is going on in our neck of the woods. So our neck of the woods is basically genetic technologies. We're a company that is able to crack open deadly viruses, scoop out their viral DNA, and put in other types of DNA. It's really the difference between getting a virus on your computer and getting an update. Viruses do something bad, updates do something good, but actually to your computer, they're just about the same thing. Well, it turns out that we can do that in human beings right now as well. Basically, we can take deadly viruses that bring in a whole bunch of malevolent DNA, and we can chop that DNA out, and instead we can put in things that make you better. That's the basic idea behind AGT. It's a new technology, and what we're so excited about is that there's so many opportunities to treat diseases that were formerly untreatable, or to apply this technology to relieve suffering out there from existing diseases, and to even end early deaths from a lot of different diseases that are terminal right now, that we can use this technology to mitigate the underlying issues of these diseases and to end their impact on human beings. Now, it's not all going to happen in a day, but a lot is happening right now. And what this talk is about is to give you a sense of how is this progressing, and what are we working on right now, and when is all this stuff going to come? So I'm going to give you my vision of that situation. So that's what it is about AGT. Now, what kicked off this whole revolution in gene technologies? Well, in my mind, it was somewhat the Human Genome Project. This started in 1990. It was supposed to be a 15-year project. They actually got it completed in 2002, which means it was 3 years ahead of schedule. And the plan was just to figure out for one person what are the order of their amino acids in their DNA. We're going to talk a little bit more about amino acids later, but basically your whole body is coded in ACTG, and they form genes, which are strings of these things in a particular order, which could be, small, 500 of these things to thousands of these things in a single gene. But basically, that is what controls your body. And the Human Genome Project, what it got us was the sequence for one human being. Now, a lot of people ask me, well, once we sequenced it, how come all the diseases didn't go away? Well, we knew the order of these ACTGs, but actually back in 1990, we didn't know much about what each one of these genes did. We didn't even know how many genes there were total. Now, we really have a good sense for that. Your genetic code is extremely complex, and because of the number of genes you have, somewhere between maybe 22,000, 25,000, and the way they interact with one another, it's a very, very complex system of interaction that makes you. But the fact is that every day we learn more. There's basic research going out there, most of it government funded, that is allowing us to understand better what all these genes do, and also what kind of diseases come when these genes malfunction. So it's that information that company like AGT can action, because we have this ability to go ahead and send in new genes into cells that may be missing genes that you need. We also have the ability to go in and turn off genes that may be turned on that you shouldn't have, that are also causing you problems. And so it's our ability to reprogram you to make you better that is the core of AGT's technology. But it's the knowledge of all these different genes and how they work that allow us to design drugs that can improve the human condition. So the Genome Project was really the kickoff of this, and it not only put the whole human genome in the spotlight and the whole idea of genetic medicine, but I think even more importantly, it kicked off a huge demand for all of the equipment that is utilized in companies like AGT. And what we saw is all that equipment and all that capability just started to drop in price while going up in capabilities. That meant that we could be even more effective at what we were doing. So there was a huge decrease in the cost of PCR, gene sequencing, even gene synthesis. All different types of gene knockout technologies allowed us to do all sorts of things with animal models. And this is what formed the picks and shovels of a revolution that you're about to experience in healthcare. So, what did that do? It kicked off really the gold rush. That's what I'm talking about here, is that there was a huge demand for sequencing technologies and services, high-tech equipment for genomic research. There was an explosion of basic research on genetic pathways of cells and disease. That was because of all this equipment and the costs coming down and more people adopting this equipment and more people using these services. Essentially, it was just this explosion, this snowball rolling downhill that allowed people to do an amazing amount of experimentation and generate a bunch of data on what's going on in your body. So we got experimental data, we got sequence data, we got patient data, we got this huge explosion of data. And a lot of people think that precision medicine is about analyzing that data and finding out what drugs work and what drugs don't work, or individualizing a treatment regimen for you based on your genetic expression, which of these drugs would work and which drugs wouldn't work. I think that's part of precision medicine, but I actually think that there's more. So, but let's talk about the data for a moment. It's extremely useful data. It's data that exists in a $10 trillion market. Imagine that. Healthcare worldwide is $10 trillion. That includes everything. So it's not only that $1 trillion worth of pharmaceuticals that you hear about all the time, but it's really the fact that people have to go to doctors to get advice, to get diagnoses, to get treatments, to get checked back up again to make sure these treatments are working. I mean, there's a lot of stuff going on there that is more than just drugs that you're taking. So the $10 trillion market is spread across all of those different services. And the aspect of this that we're talking about with precision medicine, and where a lot of the benefits that people think will come from precision medicine, is it's going to allow us to get more accurate diagnoses. It's going to also provide us opportunities to predict things that are going to go wrong with you. So if we can go down into your genes and we can see exactly what type of expression you have or which types of mutations you have, we could actually make predictions about the diseases that you may encounter in the future. So at its best, it means that with precision medicine, with all this new genetic testing, with all this data out there establishing patterns for human beings and what tends to happen when you have certain mutations or certain expression patterns in your gene, we're able to make these better predictions, make these better diagnoses, and we might be able to link you in a timely way to more effective types of therapies. This obviously is going to bring efficiencies to the whole system. I think that's very important, and that's a very nice benefit of that. Instead of you trying 4 or 5 drugs before you hit the one that actually works for you, maybe you'll get it in the first try. So there's another sort of other edge of the second edge of the sword here, and that is that in some cases this may not necessarily have benefits to the patients. You can see how this data also will determine statistically which drugs are likely to work for you. And certain drugs, let's say it only has a 5% chance of curing you. Well, they may say, well, that's not much of a chance, it isn't worth trying that, right? So it could actually be an opportunity for insurance companies to deny you low probability therapies. Now, low probability therapies are not necessarily something you want to try on everybody as their first try, but if it's the only thing that has any hope, well, maybe a 5% chance of doing something really positive for you think is important enough that it should be included. Well, that's a debate that's going to go on, and this is going to be a lot of data that's going to allow insurance companies to bring data into that debate. The other issue that I see with all of this genetic testing is that if there's a predictive value of this genetic testing, and it's able to tell you things like, oh, you have an increased chance of getting Alzheimer's, you have an increased chance of getting cancer. Well, if you can't do anything about those diagnoses or those predictions, if it isn't actionable information, it's just one more thing for you to worry about. And actually, this is my personal belief, but I think that worrying about disease actually impacts disease. We know for a fact that if you have confidence in your doctor or if you believe in your treatment, you have a better chance of a positive outcome. In other words, we already know that there can be a 35% placebo effect in your treatment just by virtue of the fact that you believe you're going to be okay. Well, guess what? I believe that there's the other side of that as well. And that is that if you keep thinking about how you might get sick or how you are going to get sick or how there's something inevitable in your future, you're actually causing stress and inflammation that can help to bring on those diseases. So what I'd say is that I'm not a big fan of getting your genetic testing done unless there's something in there that you're looking for specifically. I think that could be important if you're trying to figure out whether a particular drug may work on you, or to figure out what's driving your current situation, if it's time to do something about it. But to look in your genes and decide that you have a chance of this or a chance of that, I'm not sure whether I'm all that excited about everybody having that information. I think you'd be better off spending your time meditating and relaxing, to tell you the truth, and not worrying about what may go wrong in your body. But whatever, that's up to you. But I think the critical thing that we need is we need to marry together all of this precision data, this precision medicine, this predictive information, these really accurate diagnoses with really powerful drugs that can fix the problems that you encounter. And I think that that's what's happening in gene and cell therapy, in what we call genetic medicine sometimes. I think that there is an incredible variety of solutions that are coming that are based on genetics, that are driven by molecular biology of cells, that has to do with actually fixing mutations or fixing problems that are in the cells in your body in the clinic, basically in vivo, in order to, let's say, cut out the drivers of diseases, right? How can we chop off cancer at the knees so that it can't grow as fast in your body? Well, there's a genetic solution to that. Or it could be replacing enzymes or proteins that you're not making that are resulting in parts of your cellular biology not working as well or breaking down. Well, can we go ahead and put in genes that upregulate those proteins and enzymes? The answer is yes. And I think what we're finding is that genetic technologies, the kind of things that AGT does, is increasing in efficacy, increasing in power, and also coming down in cost. This sounds a lot like the computer revolution. You probably remember the first time you saw a PC. It was a long time before the first time you saw a smartphone, right? But actually, a lot of people who saw the PC predicted the smartphone. Now, they couldn't tell you when it was going to come, but they knew it was coming. They knew it was coming because that is the nature of high tech. It just keeps getting better and better and better, smaller and smaller and smaller, and less costly as well. Better plus less costly, that means, essentially almost like a steamroller, that's just heading down the road. You can't stop it. And what AGT is trying to do is we've discovered a lot of technology that's in this pattern, and we plan to exploit it for your benefit. But the main point of what AGT does is to try to find solutions where there are none right now. So if you do take something that predicts you're going to get Alzheimer's, we'd love to supply something that will fix that just in case you ever encounter it. So you can go back to meditating instead of worrying about Alzheimer's. All right. Right now I'm going to sort of delve into some descriptions of technology. And the reason I'm doing this is I think that although you may not be able to build a car, you certainly can drive a car. You may not be able to build a computer, but you can certainly understand what a computer does. And it's the same thing with molecular biology and genetics and viral vectors and all the things that AGT does. So what I'd like to do is to give you kind of what I think of as a layman's explanation of what's going on in genetics, virology, and cellular biology that would help you to understand why I'm such a strong believer in the fact that AGT and other companies like AGT are going to be able to deliver an amazing variety of almost miracle cures to things that are currently completely untreatable or incurable. But it really will help you to understand a little bit about how your body works, and then the technologies that we use to change how your body works and how that impacts the diseases that you may encounter in your lifetime. So let's start off with genetics. So in my eyes, you are nothing but a giant stack of organic computers collaborating with each other in order to form you. You have nerve cells in the brain that transfer around electrical impulses and that give you your thoughts. You have cells in the stomach that dissolve food with hydrochloric acid or whatever type of acid that they put out in your stomach in order to break down food. You have other cells that can extract nutrients from it. You have cells that allow you to move, muscles that take electrical impulses. You have retinal cells that are actually light sensitive and convert that into electricity that goes into your brain that allows you to form images. But each one of your cells runs off of the same thing. It runs off of your DNA. That's right. We can take any cell in your body. It's got the exact same DNA as every other cell. And what's going on is that these cells differentiate, and I'm going to tell you about how they do that later. But basically, each one of your cells is specialized, and as a collection, it's able to make a human being, to make you. So all these cells collaborate together, they communicate together, but each one of them individually is essentially an organic computer. And what do I mean by organic computer? Well, let's look at computers for a second. So you're all familiar with the PC, and you've probably heard that what the PC does is it processes zeros and ones. And that's actually exactly what it does. Now, it looks more sophisticated on the surface, but everything that you see going on is actually just a conversion of these zeros and ones into things like the images on your screen, or even impulses that go down a wire to a servo motor that moves a robot, or that are zeros and ones that are coming from an A to D converter, something that is a sensor that measures the temperature in the room, or is even as sophisticated as the CCD in this camera that we're using right now, that it takes those electrical impulses, it converts them to zeros and ones, and that's what your computer is working on. And what can your computer do? Nothing but change those zeros and ones into something else. It has statements that say, oh, if we get this pattern, do that. Or, you know, if I get this from this sensor, then readjust this servo motor. But that's basically all that's going on in a computer. The zeros and ones are what we call binary numbers. You actually can form numbers from zeros and ones that you can convert into base 10, something that's more familiar to you. But essentially that's all it is. Computers work with numbers. Now the cell is way more sophisticated than that. And why do I say that? Well, the reason I say that is because, first of all, it works in base 4. So there are 4 symbols that make up the numbers that your cell processes. It's A, C, T, and G. This is what your genes are made of. And your genes can be of any length. So you could have small genes that are quite small, or you can have larger genes that are quite large. It's not even a fixed length of a gene. So we have basically the different patterns of those 4 amino acids determine what your cell does. Now what your cell does is much more than just add these things together like a computer does. No, it actually converts those to enzymes or proteins or building blocks of the cell itself. In other words, everything that your cell does traces back to a gene that instructs that cell how to carry out that operation. But what's amazing about your cells is that they produce things that allow them to split and build another cell. Try to get your computer to do that. impossible, right? They actually work in the materials they're made of. I mean, it's just remarkable. If the smartest microprocessor on Earth could understand what your cells does, it would be incredibly jealous and be red with envy about what your cell can do. Now, we don't even understand the full breadth of what your cell can do, but we're starting to isolate a whole bunch of genes that do specific things, and that is actionable. If we can change those genes, we can change the outcomes. If we change what's going on in the cell in terms of the software, if we change that software, we change what's going on in the cell. Could that have an impact on cancer? You bet. You know that there are certain genes in your cells that exist in every single cell in your body that we call oncogenes. Why would you have oncogenes, cancer genes, inside your cell? Well, there's got to be some reason, right? It's got to be evolutionary. You know, maybe back in caveman days or whatever, every once in a while somebody had a mutation and it grew into something useful. You know, thumbs, another organ that does something, a better eyeball. I mean, mutations are what moved us forward as a species. Now, you don't see mutations in your lifetime because they take millions of years and lots of deaths, right, from bad mutations before you get one good mutation that actually does something positive. And if that positive thing allows that creature, or let's see that it forms a new version of some sort of animal, and that animal is a little bit better than the last animal, and it survives a little bit longer, it has a few more babies, those genes get passed on, it starts to create a community of these things, and this is how we evolved. So cancer may have actually been part of our evolution, but it's in every cell that we have. Well, that's not dangerous. That's not a big deal. I mean, you actually have cancer genes that trigger every once in a while, and they may cause that cell to go cancerous. This is why I was saying, don't stress out about cancer. Just relax, and your body will take care of it. Your immune system actually eliminates cancer every day. This is normal. It never turns into anything that you would call cancer. It's just normal operating of the body, but it's those cancer genes that are turning on. So you could imagine that if a cancer gene is turned on, if there was a way to turn it off, that might be beneficial. So you're starting to understand what it is that AGT does. So we get into that software, that ACTG, and we change it so that we turn off things that shouldn't be on or turn on things that should be on. So next thing I want to explain to you is viruses. So viruses are what we call a vector in our case. It is the way that we carry new genetic information into you. It's the way that we reprogram those ACTGs, those genes in your body. And the fact is that viruses have been doing exactly this for millions of years. Viruses themselves have actually evolved into more and more sophisticated viruses. They have sort of an evolution that has yielded superior viruses over time that have managed to thrive within the animal and human species. And what viruses basically do is they carry small amounts of genetic information. What do I mean by that? Those ACTGs into your body, and they reprogram your cells. And let me show you what the process of that is. So for you to understand that, the first thing you need to understand is the cell. And I'm going to grossly oversimplify the cell just to make it understandable here. What I put up right now is a cell. A cell is essentially, you could just think of it as like a basketball. Of course, it's much smaller than that. But inside that basketball is the contents of the cell, and the outside of that basketball is the membrane. I actually like to call that a factory, because I think a cell is a lot like a factory. And one of the things a factory has is a manager's office. Well, in the cell, that's called the nucleus. So there's a little ball inside that bigger ball, and that is what we call the manager's office, or the nucleus. And of course, inside the manager's office is the manager. And this is the key to differentiating cells. You see, you have a manager in each cell that understands exactly which part of your DNA applies to that cell. In other words, the shop manager knows what parts of the instructions, the overall instructions for your whole body, applies to just his shop floor. So he has a copy of your entire DNA inside his office. It's in a safe that only he can get to. And he goes through that DNA every day, and he knows which instructions in that DNA, you can think of genes as almost recipes, which of those instructions need to be carried out by that shop in order to keep that shop healthy and to turn out the products that it needs to turn out. Okay, so what he is doing is he is providing the proper instructions to the shop floor, to the machinists, for them to execute every single day. They may be rebuilding parts of the cell, or they may be carrying out functions like making light-sensitive proteins, or making acid in your stomach, or making other enzymes that go around your blood, or being T cells. I mean, everything essentially comes out of that instruction set, and it's that manager who knows which instructions apply to his particular shop. So the way he instructs his shop is he turns out something called messenger RNA. But you can just think of those as messages. They're teeny little copies of genes. Now they're structured a little bit different. Your genes are in DNA, which is a double-stranded architecture, and the reason it's double-stranded is extremely stable. But what the manager does is he kind of splits those open and he makes a copy of one side. That's what RNA looks like. He makes that copy, and that is the message that goes out to the shop floor to make the thing that gene is instructions for. I mean, think of that gene as a recipe for an enzyme or a protein or anything else. So he sends out those messages, and the shop doesn't know what they're getting. They just pick up the message and they do it. So that's the basic functioning of a healthy cell. All day long the manager is going through his DNA and he's saying, well, this is something my cell needs to make. He puts out a message. Here's another thing my cell needs to make. He puts out a message. And the shop floor executes those messages. They're not real smart. Whatever message comes by, that's what they're going to make. And in fact, we can put other messages in there to make other things. And that's exactly what viruses do. So along comes a virus. Inside the virus is DNA. And when the virus docks with a cell, what it does is it just dumps all that DNA on the shop floor. Well, it's actually RNA, let's call it in most cases. But the bottom line is that it puts a bunch of fake messages on the shop floor. And remember I told you that those shop workers, they're not that smart, right? They operate the machines, but whatever instruction they see, they're going to execute. Well, guess what? They can't tell the difference between instructions from a virus and instructions from the manager's office. So if the closest instruction is one from the virus, they're going to execute it. And viruses are really good at overwhelming the normal instructions with their instructions. And most viruses do the same thing, which is they put instructions in there to build more copies of themselves. And guess what? Even though the cell has never done it before, with these new instructions, it can do exactly that. It will go ahead and build new things that it's never seen before, and they will be copies of those viruses. Now, once they've made enough copies of the virus, what they're doing is they're actually stealing all of the critical natural resources of the cell. Instead of doing what the cell's supposed to do, they do this essentially production and packaging of viral particles. And eventually they use up everything of use in the cell, and the cell becomes unstable and it does what we call lysis, but basically it falls apart. So that cell, once it's used up, is going to fall apart, and those viruses, particles, are going to escape, and guess what they do? They go on and attack other cells. So this is how viruses work. They come in and they reprogram your cell to do their bidding, something malevolent, right? Remember, that's the difference between a virus on your computer and an update on your computer, that the virus is bringing in something that serves the virus's purpose, not necessarily your purpose. That type of virus that I just described is something I call the smash and grab virus. And it's the most common type of virus out there. It's like the colds, the flus, Ebola, a lot of different viruses that you've heard of. They work this way. And what makes them what I call smash and grab is that they destroy the factory that they built the copies in. So once a virus is in your cell, that cell is a goner. It may take a little while for it to produce enough virus that the cell breaks down and releases those virus particles, but it's inevitable that it's going to do it. This is one of the reasons that a cold or a flu virus is so easy for your immune system to get on top of. of course it's growing geometrically, but your immune system also is able to react geometrically, even faster than a virus can spread. As a matter of fact, the reason that Ebola is so deadly and a cold is not so deadly is not the fact that you can't react to it. You can react to it the same way. The problem is that a cold tends to stay places where damage there isn't going to kill you, whereas Ebola tends to work in the membranes of your organs, in these cells, and as it does the damage, it can actually, in the early stages, do enough damage to you that it could kill you. A cold virus would have a very hard time doing that. But your body reacts the same way, and the viruses are actually very similar. They get into your cell, they hijack that cell, they make it do the work of reproducing the virus, and then they blow up that cell and go on to other cells. So I said they're easier to get on top of because they don't hide. And if they're hiding for a very little period of time, right? They only live in your body as long as there are cells that are growing that virus, and as long as your immune system hasn't spotted those viral particles and washed them out of your blood. But there's a way more clever virus out there. It's called an integrating virus. And there's a very famous integrating virus that I'm sure you've heard of called HIV. It's the virus that can cause AIDS. Now, HIV is not a smash and grab virus. It's quite different. It has genes inside of it, just like, or let's say, recombinant DNA, something that can reprogram the cell. It hijacks the cell also, but it hijacks it in a much more sophisticated way. I call the HIV virus a super spy virus or a 007 virus, because what it does is when it docks with your cell, it doesn't just dump a whole bunch of instructions on the shop floor and get the whole shop working on making copies of HIV. It could do that, but then HIV would be like, a cold. It would explode the cell and it wouldn't hide very effectively from your immune system. No, instead what it does is it creates a little piece of DNA, and it actually sneaks across the shop floor, breaks into the manager's office, picks the lock on the DNA safe, and sticks in new instructions. And it even tags it to let the shop manager know, hey, this DNA is for your shop. So what happens is the manager just goes about his normal business, and he's sending out his normal messages that make the cell operate normally. But the difference is every once in a while he sends out another message, a message from HIV that says, build another viron. And it does that. It builds another viron, and it sends that viron out to infect another cell. You notice this is a little bit different than the smash and grab virus. One is it doesn't spread quite as quickly from cell to cell. It's a slow-moving virus. But it can live in your cells for decades. That means it has plenty of time to do its work. And in fact, because of how it moves slowly, and it slowly co-ops or overtakes or corrupts your entire body, it is a virus that is extremely tricky to treat. It's hiding in your genes, and it can stay there and show no symptoms for as much as a decade. A lot of people don't know they have HIV until one day they can't get rid of the cold or a flu, and then they go into a hospital because it turns into pneumonia, and they do a test on them and they say, sorry to tell you, you have HIV. And that is the nature of HIV. It slowly takes over the body, and it hides actually in your genes. Well, it turns out that HIV is really doing a permanent reprogramming of the cells that it infects. And if it wasn't doing something so horrible with the cells, i.e. installing the AIDS genome, the HIV genome, it actually could do something very useful. Maybe it could install a gene that you need. Well, that's exactly what we do. We hijack the hijacker. Now, what do I mean by that? We take the HIV virus, and we actually can crack that virus open. Boom. And we can extract AIDS. In other words, we can scoop out the viral DNA, and we can just throw that away. Now we have this empty shell that can still deliver genes to your cells. And that's exactly what we do with it. we can take a gene that you need, a beneficial gene, and we can go ahead and install that in that capsule. So we use the virus's native capability of delivering genes to deliver good genes instead of bad genes. Sound a little bit like an update on your computer as opposed to a virus on your computer? That's exactly what it is. Now, not only can we install genes that you don't have, or that genes that you need to turn on, but we can actually install something that is called a siRNA. It's a gene that will create what are called short interrupting RNAs. You don't need to understand that, but the basic idea is that it creates something that shuts down a gene that you have. So we can turn on a gene that you need, or we can turn off a gene that's firing that shouldn't be firing, or that would be better if it didn't turn on, if it wasn't working. So we can package those things in there, and we can actually put multiple genes in one viral particle. We put that particle back together, and then what we do is we're very careful to clip out all of its capability to replicate. All right, so when we take out the genes in HIV, we take away its ability to actually make copies of itself. So we have now one viral particle that can install one gene in one cell. And then in order to treat somebody, we'll go ahead and replicate that trillions of times or even more, and we'll treat an organ. We could treat a cancer tumor, we could treat blood with those viral particles without any danger that treatment could turn into a new virus and that could spread from person to person, because those viral particles are not able to replicate. That's a very important thing for you to understand about what we do right now. Now in the future, we may use replicating viruses, but for safety reasons we don't go near that right now. What we use is these viral particles that are called replication incompetent. So we're using HIV, stripped of the AIDS genome, stripped of what makes it HIV. So carving out everything that could be negative to you, and instead we're putting in its place genes that are good for you. And we're using this to start to look at a wide variety of diseases. So let me show you how this works. So here's our cell again, and here is its normal operation. It's sending out different types of messages. And one of the messages is something that you don't want. It could be that it's even HIV. It might be a command that says to the cell, make an HIV viron. So you don't want that message in there. So along comes our virus. It docks with the cell. It goes ahead and it creates a piece of DNA that it installs inside your DNA. And that new DNA, if it's a new gene that we installed, it'll start outputting a new message. All right, so maybe it'll start creating an enzyme that you're missing, and that will make you feel better. Or it could output something called an siRNA that could block an existing message. And that's exactly what an siRNA is. It's a very short string, 19 to 21 of these amino acids in a row, that exactly matches some piece of a gene that we want to turn off. Well, when that match happens, they bind together and it makes that gene product, that gene message, unusable. That message just dissolves. So since it's unusable, your cell will break it down and recycle it. So it doesn't hurt your cell, but it doesn't work. So whatever that message was that we shut off, it no longer can have an impact on the operation of your cell. So I basically explained to you the idea behind AGT's medicine, and that is that we can change the expression of your genes in a very targeted way. We can make viral particles that go to specific cells in your body, and then we can go in there and we can either turn off a gene or turn on a gene in order to mitigate disease. Now there's one other thing I want to tell you about that's really cool about what we do. We have something that you could think of as a smart fuse. So if we have a gene medicine, so we have a gene that we're going to turn on in your body, and we decide, well, it should only turn on in certain types of cells. We can put something on there called a specific promoter. A specific promoter can actually look at your cell and decide whether or not to turn on a gene. that actually specific promoters are all over your genome. But we can use those specific promoters to decide whether we're in the right cell type that we actually want to apply that medicine. What that means is if that medicine somehow accidentally ends up in a cell where we don't want it to turn on, if we have a specific promoter that can identify that proper cell, it won't turn on the drug if it's in the wrong cell. So it's like now it's a smart medicine. And the idea of making smart medicines is that ones that turn on in the right cells, or turn on in cells that only exhibit enzymes or proteins that are related to your disease that we're trying to treat. The idea of that is to narrow the effect of the drug, because most drugs that fail in the clinic are because of side effects that happen in healthy tissue. It's because when you take a pill or you get a shot, it goes all over your body, and it treats all your cells as equals. So wherever it can get into a cell, it's going to go ahead and get into that cell. It has no way of determining, gee, was this a cell that I really belong in? Well, genetic medicine is different because of this smart fuse, because of specific promoters. We can put things into our genetic medicine that determine whether that medicine turns on or not. And we can prevent it from turning on in off-target cells, in healthy cells, in the wrong organs, in the wrong place in your body. And we can make sure it does turn on if a cell exhibits the enzymes or proteins that correlate with a particular disease, or if that cell has enzymes and proteins in it that indicate it's a certain type of tissue. So for instance, we could go ahead and use a liver-specific promoter that would only turn the drug on in your liver. So if we treated your liver and a little bit escaped your liver, it would have very little effect anywhere else, because that liver-specific promoter would only allow the drug to turn on in liver tissue. Anyway, that's one of the really critical ideas behind genetic medicine, behind gene therapy, cell therapy, is that the targeting is so much better than old technologies, that what this means is that more drugs that we create in this way will actually make it through the clinic. And we're seeing a lot of evidence of that already. So, now the fun part. What is coming in your future? Well, remember what I was talking about is I thought what was important that AGT will do for precision medicine, and what other companies like AGT will do. We're not the only company out there doing it. I think we're one of the best companies, and maybe the best company doing it, but that's my opinion. And I hope that we're going to be able to prove that out as we're getting into the clinic. But the idea behind what we're doing, what Bluebird's doing, what Sangamo is doing, what a lot of these other companies, Juno and Kite, are doing in applying technologies like these, is that we can make a much wider variety of very powerful cures with very low amounts of side effects. In other words, we can make new drugs that are more efficacious and that are more likely to be able to be given to people without having serious side effects. So what's coming down the road? Well, we actually are on the eve of going into the clinic with an HIV functional cure. Now, what does that mean? A functional cure just means that it's essentially, I'm again explaining this in layman's terms, but a functional cure means it's as good as a cure, even though a scientist would look at your body and say, well, you still have a little bit of that virus, right? Well, it doesn't matter if you have a teeny bit of HIV in your body. If, in fact, you can, if you're slowly eliminating that HIV over time, like a normal immune system would eliminate a normal virus, and if that HIV cannot possibly turn into AIDS, so you'll never get a symptom of HIV, and if you're not contagious, and what about if you couldn't even recontract HIV, okay? So, the HIV functional cure is an example of an infectious disease application, but there could be many more. Maybe there's a chance of curing hepatitis B, maybe a new treatment for Ebola, maybe all different types of viruses can be hunted down and fixed this way, or that we can actually reprogram your body against diseases. So you're going to see a whole bunch of infectious disease cures come along. HIV is one of the first ones from us, But I think it's not the last one from us, and I don't think it's the last one you're going to see from this industry as well. I think you're going to see a lot of stuff. Now, the most obvious use of viral vectors, and what you're going to see is the most common out there in the industry, is monogenic diseases. Monogenic diseases, or especially monogenic loss of function diseases, are when you have a mutation in one gene that is not capable of making the proper enzyme or protein that a normal person would make, and that lack of that protein or enzyme is causing the disease. This could be anything from something that's slightly irritating like lactose intolerance to something that is really serious like phenylketonuria. Phenylketonuria is a situation where an enzyme called phenylalanine hydroxylase can't be made by a person who's got mutations in his PAH genes, his or her PAH genes. It's not a very common disease. About 1 in 13,000 kids in the United States gets that disease. And actually, it is common enough that it's one of the diseases that's tested for in every baby when they're born in the United States. They take that pinprick test with 1 drop of blood, and they look to make sure that there's normal PAH in that blood before they even feed that child, because if that child doesn't have normal PAH, they can't metabolize animal protein, and even one meal with animal protein could permanently disable them both mentally and physically, or even kill them. So it's a very serious disease, and the way they treat it right now is you just have a diet without animal protein. That has some real complications, but that's, it's more than an inconvenience. It's more than having to take lactase whenever you want to eat ice cream. It's something that really affects a person for life. And there are other monogenic diseases that are quite serious: hemophilia, beta thalassemia, alpha trypsin disorder. I mean, the list goes on for about 7,000 different diseases, and most of these diseases have no cure, or some of them have no treatment, and people just have to suffer with the symptoms and deal with going to the doctor to just alleviate some of the pain and suffering that they feel with any of these diseases. So, monogenic diseases actually, believe it or not, are responsible for 21% of the healthcare dollars that are spent out there. Even though there's 10,000 very rare diseases, when you add them all up and you look at all the problems that these people suffer with and all of the medical attention that they need, almost, or maybe a little bit more than 1/5 of healthcare spending in the United States is spent on keeping these people either alive or comfortable or fixing problems that result from that disease. So it's a very important space, and this is just a classic application of a viral vector, right? You may not believe this, but let's say that you're missing a gene and we want to order the normal human gene in order to put it into one of our viral vectors. We can actually get on the internet and we can order that online, and somebody will send it to us in a plasmid. That's how advanced this industry has become. We can actually get a copy of any gene that we want sent to us by FedEx. It comes packed in ice or whatever, and it's called a plasmid, and we can chop that plasmid up and we can insert that plasmid into an existing vector that we have, an existing viral particle that's all designed already, that already works in the type of tissue we want to put it in, or we can make a new vector and put it in. So the bottom line is that it's just a classic application of viral vectors, is to take a gene you're missing, put it into a viral vector, and then treat the part of your body that's supposed to be making that enzyme or making that protein. The theory is that if you're now making that enzyme or you're making that protein, that the disease will go away because you're no longer lacking that thing you were lacking that was causing the disease. So it's fairly simple to understand, but it is actually much more complicated to do. As a matter of fact, we're making a therapeutic right now, or really a cure right now, is our ambition for phenylketonuria, that disease that I mentioned earlier. So it isn't good enough for us to order a PAH gene over the internet, for instance. The reason being is that the PAH gene expresses at such low levels that we'd have to put so much of it into your body in order to get enough PAH to fix that disease, that the viral treatment would require so many particles that it would be prohibitively expensive, multi-millions of dollars to treat one person. But even if we could afford to do that as a society, treat everybody with PKU for millions and millions of dollars, it wouldn't matter, because that many viral particles put into your body at one time is toxic. It would kill you anyway. So what we have to do is figure out a way where we can put in a manageable number of viral particles, but still bring in enough PAH expression that it could provide enough PAH in your blood to metabolize animal proteins the normal way. Well, the researchers in the AGT lab have discovered and patented a way to make a human PAH gene that expresses at 1,000 times its normal level. So we think we're on track for providing a cure for phenylketonuria. However, this just shows you some of the complexities that come with each one of these individual monogenic diseases. So although I believe strongly that they're all going to be fixed eventually, it's going to take time. And each one of these things requires a certain amount of creativity and a certain amount of new ideas and discoveries and sort of new designs, and taking the tools we have and and combining them in unique ways in order to cure them. But over time, we're going to knock out probably 7,000 to 10,000 monogenic diseases that are a huge part of the healthcare dollar right now. The other thing you're going to find, which is particularly exciting, I think, is that cures for cancer are coming. I'm so confident of that, and I've been saying for years that this would happen, and I've actually been watching things like CAR T. So CAR T is a way that they're using right now to treat blood cancers. So carcinogenic B cells that make up leukemias or myeloid leukemias can be eliminated from your body by treating T cells with something called a chimeric antigen receptor. That's where it gets its name, chimeric antigen receptor -T for T cells. And what scientists have figured out at other companies, we don't do CAR T, but what they found out is that they can reprogram your T cells to be highly effective hunter-killer cells of carcinogenic B cells. And so they can go ahead and take out T cells out of your body, treat them with viral vectors the same way that we do make viral vectors. As a matter of fact, CAR T uses lentiviruses, the same viral backbone that AGT drugs use. And what they do is, after they pull these cells out and reprogram them, they're putting a new antigen receptor on those T cells, which is hunting down B cells. And T cells are amazing at killing other cells. If they detect a cell that stimulates that antigen receptor, they'll eat it and kill it. And the only downside in my mind for CAR T is that CAR T is making an unnatural type of T cell. Instead of having a monospecific T cell with one antigen receptor, they're putting a second receptor on there. So that has some potential dangers. The other thing is that when they take these T cells and they put them into your body, there can be a reaction that is of appropriate level, or there can be an underreaction or an overreaction. Overreaction can be serious, even deadly. But the bottom line is that they're now taking deadly cancers, I mean deadly blood cancers where you're guaranteed to die, and they're providing a new technique in gene therapy using these something called cell therapy. They're taking viral vectors, treating T cells, putting them into your body, and they're providing something that has a very high cure rate. Although it sometimes can cause some side effects, it's still a worthwhile drug, because in a lot of people that have no hope, it gives them hope again. So that's one of the first cancer cures that you're going to see is CAR T. But we think it's going to get way, way better in the future. As a matter of fact, we're pursuing a whole other immune oncology approach that I'll tell you about in some other video sometime. But it's going to turn CAR T on its head. So instead of treating your T cells and making them super T cells that are hunting down cancer in your body, which is a great idea, but you could also think of these super T cells as being Franken cells, right? They're modified, and your immune system is a very sensitive, complicated part of your body. So we're not really excited about modifying your immune system. However, we would like to take advantage of the immune system's ability to eat cancer, right? But our theory is treat the cancer instead of the immune system. And we've found a way to make cancer so attractive to your natural immune system that it chews it up just like CAR T without changing your immune system one bit. That's some exciting stuff that's coming from AGT in the future. So keep your eyes out for that. That's a very important part of the research we're doing. But bottom line is that either we're going to do it or some other company's going to do it, and we're going to start seeing a huge number of solutions for infectious disease, cancer, monogenic diseases, and in this new powerful modality for drug development, we're going to create solutions to problems right now that can only be treated. And what do I mean by that? Well, it turns out that there are treatments out there that will have a little bit of a beneficial effect in certain types of diseases, but actually are unable to cure them. And in fact, if you look at the overall market of drugs, about $500 billion worth of drug revenue every year is for those types of treatments, and I think that's going to change quite a bit. So what you're going to see is, instead of spending $100,000 in order to get an extra few weeks of life or an extra 6 weeks of life or whatever, which, believe it or not, in some terminal diseases, that's exactly what you get from a $100,000 treatment. Now, why do people still take them? Because there's hopes you could get more. And we're hopeful creatures. And we want to survive. And I think that's a good thing. It's one of the reasons we dominate as a species, is because we're really good at trying everything in order to survive. But the reality of those drugs is that for most people, they don't get much extra overall life. And they get palliative treatments instead of curative treatments. They get lifelong drug regimens instead of one drug that cures it up permanently. Well, this industry is that we're involved in right now, this genetic medicine, this gene and cell therapy, has the ability to completely change that equation. We're going to be able to cure diseases that were formerly either completely untreatable or at least were incurable. Where you had to take a drug for life, like I was telling you with HIV. We think we're going to make it so that you take one treatment from us and you don't have to take HIV drugs for the rest of your life. So also in this area is a promise of less expensive drugs. Now, by less expensive, I mean overall. Right? It's not like a bunch of drugs are going to come out that are going to be $1 each and cure cancer. No, what it means is that if you compare them to the cost of existing drugs, it's going to be cheaper to cure you than it used to be to just treat you. And I'm going to get to an illustration of that later. So with efficacy up and treatment costs down, this is really beneficial to healthcare on every level, even on a policy level. And you're going to see all sorts of new policy and ethical issues, most of them good. In other words, we're going to find ways to make the healthcare system much more efficient by curing you and making you feel a lot better at a cheaper price overall. For instance, with HIV, maybe instead of taking $500,000 worth of what are called highly active antiretroviral therapy drugs for life, a daily pill that has some side effects and costs $500,000 to keep a patient alive for life, maybe we'll be giving you a $200,000 treatment where you won't have to worry about that anymore. So, and you won't have the side effects as well. So it'll have other benefits in terms of some of the problems that we see in people that are on long-term antiretroviral therapy, such as early aging, bone density issues, cardiopulmonary events, increased occurrences of cancer, and other types of things that are associated with long-term chemotherapy, highly active antiretroviral therapy for HIV. So we can reduce the pain of treatment, we can increase the efficacy, and we can really make this a better experience and a cheaper experience for anybody that gets a disease. So, but I think some of the ethical issues are going to be, and this is going to surprise you, how are we going to deal with the fact that people live longer? You may be planning for a retirement that starts at age 60 or 65 or 70 or 75. Well, what if you were going to live to 120? And I actually believe that sometime in the next few decades, we're going to experience a decade or two, It'll start sometime in the next few decades. We'll experience a decade or two where nobody will die from cancer, nobody will die from infectious disease. It'll be very rare that anybody dies from anything besides just old age, total failure of their organs, or a car accident, or skydiving accident, or a skiing accident, or something like that. That's going to be very interesting, and it's going to be a profound impact on the healthcare system. But that's ways off in the future. Right now, the news is mostly good. It's going to be new cures and new opportunities for you to feel better. So when is it going to happen? Well, I think the look-back moment in this industry is probably in about 10 years. By look-back moment, I think of it as sort of like the way you feel about your smartphone or the internet, where you go, how did we ever live without this? GPS on our phones, they can get us anywhere, or tell us what restaurants are around that we want to eat at, or whatever. We got used to this technology fast, but when you think about it, 20 years ago, we didn't have anything like that. And right now, if you thought about losing your iPhone or your smartphone or whatever, you'd be like, oh my gosh, how could I ever live without that? But the fact is, you could live without it, believe it or not. But we're going to have that same look-back moment in gene therapy where you're wondering, how did we ever live without gene therapy? And you're going to really mean it, because it's going to be curing deadly diseases. You're going to realize that before gene therapy, if I got a 4-centimeter tumor in my liver, I was a goner, and now I'm not. It's just treated. I can actually live with this technology, and without it, I couldn't live. I think that look-back moment is really only about 10 to 15 years away. At that look-back moment, cancers are going to be rarely terminal, provided they're caught and diagnosed and addressed, treated basically. But here's the cool part. We're not going to be using radiation and chemotherapy anymore. That's going to go the way of bloodletting and leeches. I promise you that. That's coming, and it's coming soon. The other thing is a bunch of deadly diseases that you hear about every once in a while that are circling the globe. Epidemics like AIDS are going to end. They're going to become curable. Ebola, Zika, hepatitis possibly, AIDS. These diseases are going to disappear, sort of like they did some of the really horrible diseases in the last century disappeared when vaccines came on the scene. Yeah, that's how big this whole genetic medicine thing is. It's like the invention of antibiotics or the invention of vaccines. It's going to make a profound difference in healthcare. Autosomal and monogenic diseases. There's a lot of these diseases to go after. There's only a handful of companies that are in this space right now, or dozens of companies that are in this space. But trust me, these are all diseases that can be treated efficiently, where we can come up with drugs that are cost effective for treating those diseases. So it's going to take a long time, but it's going to get done. Degenerative and neurological diseases. Okay, these are the ones that are going to take a little bit longer to address, and that has to do with sort of the fundamental technology itself. Right now, we're great at treating limited parts of your body, but if you have something where we have to change the programming in your whole body, that's a ways off right now. We can treat an organ with a virus, and we can get to 20 to 60% of the cells, and in a lot of diseases, that's plenty. But let's say that you've got a problem where your nervous system is breaking down, and we have to get to every nerve in your body. Well, if there's certain places, if it's limited to a local spot where we can get to it and we can get a high percentage of the cells with the existing technology, with the existing viral vectors, well, it might actually be addressable with current technology. But if it requires really every muscle fiber or every nerve fiber in your body or every nerve in your brain to be treated, the technology hasn't matured that much yet. But this is something I can promise you, is it's getting better and better every day. So it will get to that point. It will get to the point where when we want to reprogram your body, we can get to every single cell in your body, and we can get it in, we can improve the targeting and improve the safety so that we can not only get to every cell in your body, but we can target only the cells that require that drug and only turn it on in those cells, and we can do that reliably time and time again. So all of these diseases will eventually be addressed. And I think that's one of the most wonderful things about this whole new drug development modality. This is really high tech. It's like digital just came to drug development. And I come from the computer industry. And one of the things that I experienced in 40 years in the computer industry is that if you can dream it, you can do it. So if you had a dream for what a computer could do in the future, You may not be able to predict exactly when you're going to get there, but you knew you would get there. And that's been the reality time and time again. It's true about computers. It's true about this new drug development modality, this new ability to reprogram the human computer. It's almost without limits. It has plenty of limits today, but the future promises to remove a lot of those stumbling blocks and improve these technologies in ways where we'll be able to address almost anything. That's a very exciting outlook. And why am I so confident of this? Well, I'm confident of it because I experienced these sort of trends in computers for over 40 years. But I've also now been in gene technologies for 10 years, and I've seen that it follows the exact same pattern of some of the other high-tech industries that I've been involved with computers. I saw my first computer in the 7th grade. When I saw that computer, I realized that was going to be huge. I said, computers are going to do all the boring things that we have to do right now by hand, like adding and multiplying and keeping track of stuff. And then my father is an MIT graduate, and he used to take me to open houses there, and I saw these early robots that they called turtles that could run around the floor on servo motors. And I realized, wow, computers will be able to control these devices, so we're going to have robotics that are going to actually be able to physically do things in the world. And then I saw sensor technology and A to D converters. And I know this is hard to believe, but even as a high school student, I knew that computers and robotics were going to be as big as they are now. I knew that was a 100-year industry. I could see all those things were coming. It was what attracted me into computers. I just loved the practicality of them. Well, it also attracted me to software, because that's what drives a computer revolution, and I saw the technology of that improve. And then I could also see another trend in my life. I was around when the internet started to become popular. As a matter of fact, I was at Apple at the time when we used to use the internet to send most of our messaging around the world before even AOL came on the scene. As a matter of fact, some people don't realize that, but AOL used to be something called Apple Link. Apple Link was how we communicated with our international subsidiaries, and we used to send these emails, which was a big deal back then, all around the globe, and they'd sit in mailboxes and people would retrieve them, and it went over the internet. Now the internet, of course, has developed quite a bit. Some people didn't realize that it would have such a big impact on us, but you could tell right away. I mean, if you really thought about these things, you knew what it was going to do to the publishing and media industry. You knew what it was going to do in terms of people starting to interact electronically with one another. You could see how it was going to join the globe together almost into one international community. You could see that it was something that was here to stay, that was just going to get bigger, better, faster, and do more and more and become a bigger part of our lives. That's why I can see this trend in genetic medicine. It's because I've been through it so many times before, and the parallels are just compelling. One parallel is the cost equation, right? We had something in computers that we called Moore's Law. In other words, we said that every year computers' power would double and the cost of these computers would go in half. So what they were talking about actually were the chips in the computer, the microprocessors or the memory chips. And in fact, Moore's Law turned out to apply really, really well to computers. But you can see from this graphic here that Moore's Law actually would have brought the cost of sequencing down along that white line. But in fact, the cost of sequencing has gone down much faster. So think about that the advances in this technology may be faster than the advances in computers. And I can give you a theory about why that is. It's because we actually can use computers as part of how we develop in this industry. So we have the benefit of that revolution helping us to drive this revolution, which is why this revolution is going even faster. And all the sequencing equipment that you're talking about is designed on computers, and in fact they contain computers, so they themselves are computers. We have different types of computers in our lab that are different types of equipment that we use every day that are specialized computers for gene medicine development. And they parallel tools that I used to use in the computer revolution as well. So look at the old versions of talking to a computer. That one that you see over on your left is called a teletype. And in the 7th grade, I had one of those in my bedroom because I just love computers, and you could attach your phone to it, and you could dial into a mini computer, and you could get time sharing on a mini computer, and you could program. Now, not that many people when I was in the 7th grade back in the 70s had teletypes in their bedroom, but teletypes were very popular with mini computers and very common in businesses at that time. And but they looked like giant, super slow typewriters. And all they could do was type black and white print on a roll of paper inside of them. Well, they got steadily better and cheaper until now the main way we communicate with computers every day is through your cell phone. You get your email there, you talk with your friends. It's a computer that is so much more powerful than the computers I used back in the 70s, and it's in your pocket. And you can talk to it. It can actually interpret your voice, or you can point at things on the screen and move them around. That's what happened over decades in the computer revolution. Well, there's a set of tools, and one of them that's characteristic of the tools in genetic medicine is the PCR machine. So that one over on the left is an old PCR machine that probably cost $1 million and could do one experiment in a day on one particular enzyme. I don't know this for sure, but I do know that these machines cost used to cost $250,000 or more. And now what I know is that one all the way over on the right, we have one just like that in our lab. It looks about the same size as a standard desktop tower computer, right? The kind that many of you probably have on your desks or under your desks. It's about that size. But what it has in there is 48 wells. We can do 48 experiments at once. You can actually buy a version of this that does 96 wells. It has 6 different colors, so it can analyze these experiments from 6 different ways. And it's networked, so we can run these experiments from our desktop. We can actually send this data over the LAN, and our PhDs can sit at their desk and get the data electronically out of their experiments. Reams of data comes right over their LAN, right to their desk, right into Excel or in some other format where they can analyze it right away. Not like that old PCR machine where you had to do everything by hand. No, it's way, way modern. But let's compare the price. That's what's exciting. That PCR machine on the right, $11,000. So that's even a faster evolution of the tools in this science, probably than the tools I experienced in the computer revolution. So the cost trends are also similar to Moore's law. So genetic technologies are continuing to improve the efficiency of drug development. And what do I mean by that? What I mean is the cost and reliability of developing new drug candidates. And in the 10 years that we've been in this business, our costs have dropped dramatically. AGT is able to quickly create drug candidates. By a drug candidate, I mean something that is worthwhile testing in mice and ultimately in the clinic. And you'd be amazed at how expensive in traditional medicine a drug candidate can be to create. They usually require taking 10,000 new molecules, screening them down to a couple that are worth testing, and only 1 in 19 of those would end up actually making it into the clinic or turning out to be a good drug. That's why discovering drugs that way can be so expensive. 10,000 molecules and getting them down to 2 different molecules that are worth testing used to take 2 years and cost $10 million just to get to that point. Well, we started off in this industry, it would take us about a year to develop a drug candidate, but now it's down to a matter of months. So we have something that's worth testing in a mouse and has a possibility of making it to the clinic, and actually a higher percentage of these drugs will make it through the clinic because they're targeted drugs that act much more narrowly on the body. So the development time per drug candidate has dropped dramatically. Looks a lot like Moore's law. Well, guess what else has dropped? The cost. So the first drug that we developed was over $1 million. That was a potential drug candidate for prostate cancer. It was a proof of concept for us that we needed to do to decide whether this technology had a future. Well, we decided it had a future, and then we kept working on it for the last 10 years. Now, it only costs us tens of thousands of dollars to do a drug candidate. Not $1 million, tens of thousands. We actually get to a go, no-go decision for our average drug candidate in under $50,000 and within months. And if we decide to progress to the clinic, so if we get enough preliminary data that we think it's going to be efficacious, we can get it into the clinic within 2 years and get to first human efficacy for about $10 million is what we estimate per drug. And that's been borne out by our HIV drug. So this is not just speculation. This is something that we're now doing every day. And we're not the only ones. But I believe we're doing this better. And the reason that we're doing it better is because we're really focused on that whole aspect of this business. We're thinking about what is the tool set that we can develop and refine that allows us to make these drug candidates quickly, because we think that there's a real hunger out there in the market for these drug candidates, and actually we think that pharma companies would embrace these new drugs and get them out to the people. Once they're de-risked, they need to be de-risked, so the drug companies need to know, these large pharma companies need to know that we've shown first human efficacy, and then they're prepared to throw in and do the rest of the clinical trials that would allow them to get out to patients and really make a difference. Now, I believe that large pharma companies are our friends in this mission. I think that we're going to actually enhance their profits. Why is that? Well, the drug industry right now is $1 trillion, but it could be much larger. And you're thinking, well, how can we afford that? Well, the reason that we can afford it is because the reason that it's only $1 trillion worth of drugs out there that are being sold every year is that's the most the world can afford for the utility that they get. But the reality is that if we cure more diseases, if we can get rid of going to having to have blood transfusions for beta thalassemia or hemophilia or whatever, well, with a drug, that's something that actually cures that condition, that's going to be a lot cheaper. So we can move some of that $10 trillion healthcare market out of being attached to machines that are purifying the blood in your body or fixing something in your body, and out to just taking a drug instead. So I think that the drug market can be much larger than $1 trillion, but we've got to deliver more. So that's why I think that this is good for pharma companies. There's a lot of sort of cross-fertilization in the high-tech industry, right? Remember I told you this whole idea that if you can dream it, you can do it. Well, what it has to do with is the fact that that in high-tech, if you don't invent a solution to a problem, somebody else will, and you can just in-license that. We had a word for that back in Silicon Valley when I used to work for Apple. We called it cooperation. In other words, our competition in some way were cooperating with us. And we didn't really worry that much about the fact that people would move from company to company, and sometimes they would bring with them, interesting technology. It wouldn't matter because we'd cross-license this stuff, and the whole industry was rising so fast that everybody was doing well. There were a whole bunch of computer companies out there, not just Dell, but Compaq and Eagle Computer and a bunch of ones that you probably never heard of. The bottom line is this whole industry was turning into this giant industry where there was none. And so this idea of cooperation was a really important driver of the industry as a whole, and something that everybody embraced in that industry. That's not what you see currently in pharma companies. When a pharma company has something, they lock it up from top to bottom, and they go through extraordinary efforts to make sure that they keep everything that they're doing top secret and patented and exclusive, and it's more like the computer industry has become. This is why Apple is suing Samsung and Samsung is suing Apple, is because the industry's not growing so fast that they're distracted by just making new markets. Well, the pharma company's gotten in a little bit of that as well. The pharma industry has got a little bit of that going on for it, but I think that's going to change with this new technology. So this is going to be an acceleration and a disruption of the entire industry. Another thing that makes this a disruptive industry, and so much like the computer industry, is the layered model of getting drugs to you. So we can be this creative organization that comes up with new software that can improve your body. Now we need to turn it into viral particles that we're going to use in treatment. Well, in the old pill manufacturing days, if we came up with a new pill, we'd have to build a factory for the human trials, because every pill was different. And that factory, it would have to be something that would be completely unique to the new drug that we were creating. Well, that's not the case with viral particles. We use lentiviruses, and there's numerous companies out there that will actually manufacture viral particles for us. That's almost like diskette duplicators back in the day of software, right? You write the software, you didn't worry about putting in $1 million diskette duplication factory into your company. No, you sent it out to a contract organization that would manufacture it for you. And the only difference between viral particles and diskettes are that viral particles carry software to the human computer, and as such they have to be FDA compliant. So diskette duplication in our industry is very, very expensive. It would cost us probably $10 million to set up our own duplication factory, but the good news is there's a bunch of them out there already. And so as a result, we can go ahead and rely on them. Let them be great at duplicating these diskettes in a way that is compliant with FDA requirements and that are safe for consumption for humans. We'll focus on our part of it, designing these new viral particles. They'll focus on their part of it, and guess what? Together we're accelerating this delivery of these new drugs to you. So you've got more companies able to cooperate in a layered model. And remember, I was talking about pharma companies. Well, what are they good at? They're good at getting those last approvals, getting the drug, set up for reimbursement, distributing it to the whole planet. So they're part of that value chain as well. One of the things that I see happening long term in this industry is that the barriers to entry are actually going to drop. And I think the cost of getting through the regulatory protocols and requirements of the FDA and other regulatory bodies around the world are going to drop. And why would that be? Because it always seems like it's been going up in the past. Well, here's the reason. We're dealing with a particle. Remember I said that there are these companies out there that will go ahead and replicate that particle for us? It's a particle that's really well understood. The only thing that we change in it is that little bit of coding of ACTG inside that particle. So the FDA already knows how that particle distributes around your body. They know if that particle in certain quantities is toxic. They know how it reacts with T cells because there's been lots of experiments out there that show how it reacts with T cells. So they have a lot of information already out there that they can take for granted in terms of if they've experimented, they've seen experiments from 5 companies where you use lentiviruses to treat T cells, that the data that's going to come back from the next 5 companies is probably going to be very similar. And eventually, once you realize it's all the same, maybe you don't even have to require it if they fit within certain parameters. Well, what that's doing is it's taking all the map of different safety issues that the FDA has to be concerned about, and it's actually covering pieces of that map with things that they already know, certain toxicities, certain behaviors in the body, and things like that. Well, the area that's not covered already by people that have gone before us in this drug industry are the things that the FDA asks us to make sure are safe when we put out a new drug. But the number of things that we have to be proved with each successive drug on a lentivirus basis, right, that's with this new technology, is less and less and less. So you're going to actually find that the regulatory barriers start to drop in this as well. And then there's the cost barriers. The cost of doing this is coming down. The equipment, think about that, $11,000. Gee whiz, you could open something up in your garage for $11,000. Now you need more equipment than that right now, but I think that the costs are going to come down so much that this may become a cottage industry someday. High schools will be training you to use that equipment because it'll be affordable in high schools. And the high school lab may be a place where you could actually create a new drug that might cure a rare disease. It's not there today, but it will be there in 50 years or even less, maybe in 20 years, maybe in 30 years. Who knows when the costs will come down that low? I only know that they will. All right. The last thing is that cures changes the whole economics of healthcare, right? That's the whole issue with the new drugs that have come out in the last 10 years, right? They were incredibly expensive to make, and then on top of that, they don't cure things necessarily. They only treat them. They don't save lives. They only extend lives, sometimes by very short amounts. Let's look at the whole drug market right now. Remember, I told you it's $1 trillion per year. And some of those drugs have reasonable utility. When I think about reasonable utility, I think of examples like aspirin, right? You go out and you buy a bottle of aspirin for, you know, $10. You get like 500 aspirin or whatever. You take one for your headache, makes your headache go away. You have a fever, it reduces your fever. You have inflammation, it reduces inflammation. Has all these positive effects. It's a good drug because guess what? The side effects are minor. No drugs have no side effects, but aspirin, you know, might be deadly to a hemophiliac, but to most people, it's a good drug. It has, it's unlikely to have serious side effects. Okay, if you're shaving and you cut yourself after you've taken an aspirin, it may take longer for the cut to heal, but it isn't going to kill you. So that's a good drug. That's a drug that actually came when they refined a natural thing that was out there in the environment that people had discovered relieved their headaches. And I think it was Bayer, the company Bayer, that refined that into aspirin, and that has been a drug that has been around for a long time, and it's a very good drug. There's another drug out there. I mean, this is a funny one to go ahead and put on this video, but you know, another drug that gives you what you pay for is Viagra, right? I don't think there are people that are taking Viagra that are complaining that it's $10 a pill, right? Because they're like, hey, what I get out of it is worth $10. And it's good in the other way in that it works on what you buy it for, and the number of side effects that it brings with it are small. And they tend to be minor side effects, you know, like having to go to the hospital if it's too effective. But the bottom line is this, that, you know, the funny thing about Viagra, it was not a cheap drug to discover because they actually thought they were doing a blood pressure medication. And it turned out it was completely ineffective at what it was designed for. But in the human testing, they found this weird side effect of erections. And in fact, you never heard the term erectile dysfunction before they invented that term, probably, for this market. In other words, erectile dysfunction was just normal old age in most cases. And Viagra made that something that we could think of as a disease, and the side effect became the main effect, and in fact the main effect became the side effect. So if you look at all the side effects for Viagra, they have to do with blood pressure. So the bottom line on that drug is it's reasonable utility. I don't think people complain about buying that drug. But then there's a lot of drugs that you would complain about. I call those low utility drugs. And a great example of a low utility drug would be certain types of monoclonal antibody treatments. Now, not all monoclonal antibody treatments are let's say, not effective enough for their price. And plus, you know, everybody has different judgments on this. But, you know, there are monoclonal antibody treatments out there for, let's say, terminal cancers, where if you are diagnosed with that terminal cancer and you are treated with that drug, it's going to cost you $100,000 for the drug. And guess what? Your overall extra survival will be. In other words, how much extra life will you get for $100,000? Well, on average, for most of these drugs, it's 6 weeks, and some are less. 6 weeks for $100,000. And think about that. In a monoclonal antibody treatment, you're going to sit for 12 days in an infusion chair in order to get that 6 weeks. So you're really only getting 4 extra weeks of out walking around. And here's another surprise for you. These things can have side effects. They can be painful. They could actually even cause your lifespan to be reduced. But you know, they're still prescribed and they're still taken, and there's a good reason for that. It's because even though the average is 6 weeks, this is essentially how it'll work for you is going to fall along some spectrum. And so when you ask your doctor, well, does that mean I'll get 6 weeks? He says no, because what you'll get out of it is unpredictable. It turns out that there are some people who get a year. Now, we don't know whether they get a year because their cancer is different or because the drug is more effective in certain people. But the bottom line is that when you look at that drug and that decision about whether you'll take that drug, especially if your insurance company will pay for it, you start weighing out like, maybe I'll get a year. Maybe something else will come along that'll make it even better a year later. Maybe I'm going to beat this cancer. And we are hopeful creatures that are very concerned about surviving, as we talked about earlier. And so, yeah, we take those treatments. $100,000 treatment that is likely to only give you 4 extra weeks of walking around out there. That's what I would call low utility. So let's talk about one of these monoclonal antibody treatments. So you're going to get 6 extra weeks, as I said. It's going to cost $100,000. But remember, with 6 extra weeks, it means that, what are we talking about? Well, this is on top of all your normal treatment. So for this cancer, you're still going to spend hundreds of thousands of dollars in the hospital. Maybe not you, but your insurance company will. And since these things don't cure, they only postpone your death, you're still going to need hospice, and you're even still going to need a funeral. I mean, that sounds like a horrible clinical way to put it, but that's the bottom line. People get these terminal cancers, and these drugs give them hope of a longer life, and they in fact give them a little bit longer life, but the bottom line is that they still pass away, and the cost is tremendous to the insurance company. Look at that. You know, if you had a terminal liver cancer and you had good insurance, you might cost the insurance company almost $500,000 just by virtue of your passing away. So let's look at how the economics changes, though, if we could talk about a cure. So the total cost of this treatment, let's say that you were to live an extra year because you took all of this $500,000 worth of treatment. Well, you know, in actuarial terms, as a rough figure, you might calculate that everybody's value to society is about $100,000 a year. In other words, your productivity and your quality of life and so forth might be on a spreadsheet might be worth $100,000. Well, you can see that the insurance company just paid $470,000 for you to live one more year, and they lost. That was not an investment in your future. It was just a cost of you dying. So they got you an extra year of life, but the overall loss on that investment was $370,000. That's just an economics way of looking at it, an economist's way. But let's now think about how is this different if we're talking about a cure. What if we could give you something that could knock this cancer back for 5 years? I think that's absolutely possible. I think we're seeing evidence that is the case, that terminal cancers will become chronic conditions. Chronic conditions meaning that, not that you have to treat them every day to keep them away, but I mean that you'll get a cancer, we'll cure that cancer, and then you'll get a different type of cancer. Because the reality is that if you get a terminal cancer, and even if you're cured of that terminal cancer, everybody knows that you have a higher chance of developing another terminal cancer later. But we'll have a knockback for that too. So each time you need to be treated and get you another 5 years of life, let's just say, and I'm just using this for argument purposes, you'll take one treatment, and that cost of that treatment may be about the same as the monoclonal antibody treatment that is available today. Well, now your hospital treatment is not you dying in a hospital. It's not you needing operations, so surgery. You don't need radiation. You don't need chemotherapy. You need a viral vector and maybe $50,000 worth of actual hospital work to get you this 5-year knockback of your cancer condition. Your total cost now is $150,000 for 5 years. Value at $100,000 a year, that's $500,000, $500,000. So in fact, you could look at this treatment as an investment in your future as opposed to just a cost of you dying. So by getting 5 extra years, you're getting a value of $500,000. If it only cost you $150,000, you almost profited from spending that money. You got $500,000 worth of life for $150,000. You got a $350,000 excess value on that transaction, while the drug company got $100,000 and the hospital got $50,000. So everybody profited. Look at the difference in cost for the insurance company. All right, this is something that's going to drive the adoption of this. The total cost under the old scenario was $470,000. The total cost under the new scenario, $150,000. So the drug company avoided spending $320,000 this year. So don't worry so much about the cost of these treatments that you're hearing about. These new treatments are going to cost $200,000, $500,000. Insurance companies won't be able to pay for them. They're already spending a lot of money on these terminal diseases. And so if you can reduce the cost, they don't care if you stay with their insurance the next year. You know, that idea of, well, they'll cure you and then you'll go to some other insurance company and pay premiums there. And they're losing that money and they did all the work and that other insurance company is getting the benefit. No, the fact is the insurance company could get the benefit in that same year. They could reduce their outlay of cash on you for that condition. It could all be justified in 1 year. So these things aren't necessarily going to be the nightmare of pricing that everybody's predicting. That's my personal feeling. And you can watch this in 10 years and we'll see if I'm right. All right. So where's the disruption going to happen? This is a really interesting part of the story, and now we're really getting into, you know, just sort of me seeing patterns and me telling you what I think is going to happen. Half of the $1 trillion market is going to move from gene technologies or from traditional medicine to gene technologies. When was the last time that you saw a $500 billion slosh from one market into another market? I can tell you right now, never. Not even the computer industry grew this fast. In 10 to 15 years, you're going to see this industry become a $500 billion industry. And where's it going to come from? It's going to come from that part of that total market that I showed you that is low utility drugs. We're going to start curing things that are only treatable. One of the examples that AGT is going to show is HIV treatment. We're going to show that it's cheaper to cure it than it is to treat it, and it's way more comfortable, and it's a higher quality of life for the patient, and it costs less in doctor's visits and hospital visits and things like that as well. So that's what's going to drive this movement. It's not us that's going to be selling it to you for $100,000. It's going to be a pharma company, but we're going to get a piece of that. That's how we're going to maintain our machine turning out these drug candidates. But the bottom line is that it's going to happen. The new growth in this industry is going to be primarily gene technologies. You're going to see that the companies like ours and Bluebird and Sangamo and Kite and Juno and Novartis actually bought their product from another company. But you know, you're going to see that a lot of the innovation is going to come from smaller biotechs like AGT. So it's going to be those companies that are creating a steady stream of new drug candidates, and companies that stay in the old modalities of biologics and small molecules and that type of drug discovery are going to be slow in comparison and expensive in comparison. So most of the growth in the future of pharmaceuticals is going to be in the gene technologies area. That's because gene technologies is more powerful and more efficient than older technologies. Pharma companies are either going to adapt or migrate. This is just the nature of markets. The bottom line is that large pharma is going to either have to adapt, in other words, become publishers of all these new drugs. I mean, because they are really in a great position to do that. They have tons of money. They can buy up these new drug candidates, and they can become like publishers that bring it out to the market. That's a great way for pharma to evolve. And in fact, if you look back in their recent history, you'll probably see that there was a trend towards that anyway, that they were becoming more of drug publishers than drug discoverers or drug developers. In other words, they were working with other companies to get their pipelines of drug candidates. Well, that's going to happen even more. So some of the pharmas will evolve, but actually I predict that some of the large pharmas will end up perishing. And why is that? Well, large pharmas rely on a small number of drugs to provide most of their revenue. And if some of those drugs turn out to be in that low utility area, some of those drugs are going to go away. And some of those pharmas aren't going to recognize that early enough and hop on the bandwagon early enough in order to get the drug candidates that obsolete the drugs that are currently providing all their revenue. So they could actually get into a situation where they cannot sustain themselves. Now, what normally happens in these types of industries is those big companies merge. So as one pharma gets really weak, another pharma will buy out its assets and combine them, and as a result you'll get one company that's still surviving, but that but that influence, that market influence is still there. So that new company is still going to have to figure out, how do we interact with all of these new drug artists, all these drug creators, sort of like if I was a major studio in Hollywood. How do I get the good movies so that I can sustain my studio's revenue? And I think that you're going to find that pharmas become these publishing companies, and whatever pharmas don't perish go into that market or go into that model. The mid-market's going to get squeezed. This is just the case in all classic developments of high-tech markets. There's no place for the mid-ground player, because you either need a big company to do it or you need a small company that's nimble to do it. The people in the middle just get crushed in the middle. And so the mid-market is going to go through a lot of consolidation, and in some cases they're going to buy up smaller companies and become those smaller companies. In other words, it doesn't mean they'll have to get small, but maybe what they're going to try to do is get into gene technologies and become one of those developers that's in this new innovative drug space. So they may cast off a lot of their old traditional types of drug discovery, and they may embrace a whole new gene technologies market. Or they may just get squeezed out of the business, or they may get bought up by pharmas. But I think that in the mid-market is really going to be some of the most difficult space to occupy. Then, as these things come down in price enough, and the equipment's cheap enough, and it's easy enough that high school labs and college labs and university professors can get into the drug development business, well, guess what? It could get as simple to do a new disease application, new cure for a disease on our platform as it is to make a new app on an iPhone right now, right? Not today, no, but in the future it could be. And so what will happen is that a lot of people that have disease knowledge are going to have a better set of tools out there where they can try innovative ideas and come up with drug candidates. So a lot of that activity, that creative activity, will disperse across the entire intellectual capital of the world. Right? I don't mean capital as in the capital of a state or the capital of a country. I mean that, all of these brilliant researchers that are all around the world are going to be able to partner with companies like AGT right now and utilize our platform, develop drugs together. But in the future, they're going to be able to just develop them right in their labs with their own tools and probably buying components from AGT. Just like, just like Apple sells an iPhone and Google sells an app for it, and Facebook sells an app, and Twitter sells an app, and Waze sells an app, or whatever, or they profit from those apps in other ways. But it could be the way that this whole industry evolves. The change, as we said, may outpace even what the computer industry did. So this may disrupt even faster than computers did, and they disrupted pretty darn fast. I watched the whole thing in my 40 years. Remember in the old days when we used to have something called a mainframe computer? Well, they still exist, believe it or not, but there's just not quite as many uses for them because better technology that was more efficient came along. The first threat to the mainframe was what? It was actually the mini computer. Many of you probably never even heard of these companies. They came and went because they turned out to be the mid-market for what? PCs. That was where the real revolution came from. It used to be that IBM and those mainframe computers, they dominated all of the computer industry. But then what happened was that mini computers came along and they had technology that was efficient in smaller businesses, and as a result, they actually were quite successful. But then their problem was that something even more efficient came along, and that was the PC. It was just enough power for one desktop. Right? Well, what does that mean? PCs are a much more scalable way to roll out your computer needs. So even if you're a major corporation, guess what? When you hire an employee, now you can buy a computer, attach them to the LAN, and you've got everything you need for them. You don't have to think about, next year I'm going to have another 10,000 employees, so I'm going to need one more mainframe to cover the 10,000 employees. When I get 10,001 employees, I need one more mainframe to cover them. No, it doesn't work that way. You can literally just bring on the amount of computing power that you need. And you even have lots of options of how to do that now. Well, what happened? Well, first of all, the mid-market got crushed. Digital and those other companies, that Prime Computer and Wang, and the idea of a mini computer that would be good for up to 100 terminals, where a mainframe would be up to 1,000 terminals. Well, that idea just wasn't necessary any longer. But the next thing that happened was the mainframe market went away, because there was a limited amount of need for these giant mainframe computers, and as a result, you didn't need 6 companies to provide them, or whatever number of companies were around at that time. There was IBM was sort of the leader in big hardware and big types of servers. These mainframe computers that became central file storage for a network of PCs. And in fact, PCs started to become pretty reliable file servers. You used to be able to build, you could then build out your centralized storage needs by just using racks and racks and racks of PC servers that were just disk servers. And in fact, all of the growth was in these microcomputer companies, and IBM actually is more of a consultant that applies networking strategies and security strategies and business strategies to the PC marketplace. They build giant networks that leverage local area networks and the internet and VPNs and things like that. They couple it together with software from a lot of these companies and some of their own software, and occasionally throw in a mainframe where it's necessary, and that's what IBM does now. So they actually adapted to this whole thing, and IBM is still around and still quite successful, and that's why. So we'll see how many drug companies can do the same thing, because the pharma industry is even more of a mess. There's a ton of giant companies out there, and they're giant companies because they have giant monopolies. At least with mainframes, if you didn't like IBM, you could go buy a Burroughs mainframe. It had advantages and disadvantages. The company had advantages and disadvantages. But if Roche has a drug that you want and it's under patent, GSK can't sell it to you. They can't compete. So that allows for there to be a lot more mainframe providers in the pharma industry. And that's why you have all these companies out there that are occupying this space. And they all have these giant monopolies, and the patents perpetuate that, and they continue to perpetuate it with different types of legislation in some cases, other types of exclusivities and rules that benefit these giant companies maintaining control over these markets, and they make an argument that it has to be that way because it takes a giant company to discover a new blockbuster drug. And I think that the reality of it is that since in a lot of cases they get those new blockbuster drugs from smaller players, biotech companies for instance, maybe that's not 100% true that we need gargantuan companies in order to make $2.1 billion investments to make one new solution to one problem. I think we're going to find out that, in fact, especially in the gene technologies area, it's not going to be necessary for that to have that level of investment and that level of power to make these solutions. There's also a lot of mid-range companies, and now there's the new upshots. These are the gene technology companies. But my prediction is this: they're going to go ahead and be responsible for most of the growth in this industry. And those other companies are going to adapt to this new reality. Because the bottom line is that if you've got something that's efficacious, you've got something of value. So it doesn't matter whether it comes from Roche or Pfizer or GSK. It only matters whether it works. And these other companies are going to help, and they're going to bring those new solutions out. So these big companies are going to be part of that value chain. They're going to be part of profiting from all these new drugs as well. But a lot of the driving for the growth of this industry is going to come from the new players that are in this gene technology space. That's my personal prediction, and I'm putting it on film right now so that, hey, someday I can look back at this myself and see, was that really right? I believe it's right because of the amazing momentum that's happening in the gene therapy area, right? there's more and more solutions that are coming out from these gene technology developers, in cell therapy, in gene therapy. And you can see the number of clinical trials just keeps going up every year. There's an obvious trend to this data from 2001 out through 2016. It's grown really almost exponentially. When you look down inside the data and you break it up into phase 1, phase 2, what you see is that these drugs are not new tries. A lot of these trials that are being filed for are actually subsequent phases for the same drug. So these drugs are moving through the approval process, and in fact now we're seeing that some of them are actually getting approved. One of the first ones that came from a major drug company, and I think was a big deal, is a drug called Strimvelis. Strimvelis is a cure for bubble boy disease. That's a popular name for ACA SCID. So it's a severe combined immunodeficiency. These kids that are born without an immune system that's able to fight off normal pathogens in their environment, and it's a horrible life for these kids. They live in plastic for as long as they're able to live, and it really only takes one pathogen, one infection, one virus to kill these children. Well, now that's not the case anymore for people that have this particular type of severe combined immune deficiency, because Strimvelis is not only available to cure that condition and put them into a normal environment, give them a quality of life, but GSK has decided to guarantee that it works. So if it doesn't cure your bubble boy disease, you get your money back. I mean, that's a tremendous assurance of their confidence in this cure. And I think it's completely rational as well. I think that the process that they're going through in repairing your bone marrow to reconstruct a normal immune system is something that they've shown to work. And now they've eliminated all the side effects that came with it, and so they were able to get this drug approved. And this is the starting gun in our industry. It shows you that a major drug company can bring out a gene therapeutic. That's a big deal. The next thing that's coming along is CAR T. It's going to take a bite out of liquid cancers. If you've got acute myeloid leukemia, acute lymphoid leukemia, the bottom line was that once it got to a certain progression, you were a goner. They could tell you how long you probably had to live. Well, it turns out now that CAR T might extend that and extend it substantially. And here's the big news. Recently, an FDA committee made a unanimous recommendation that the FDA approve a drug from Novartis that is for pediatric acute lymphoid leukemia. So in other words, kids that used to be born and there was no treatment for them and they would die very, very young from blood cancer have a hope. And that hope is going to be approved. Well, this is the beginning of something really, really big. I know it's big because I've been in this industry for the last 10 years. These are just the first drugs that you're seeing, and you're going to continue to see a drip, drip, drip of miracle cures over these next few years. But then you're going to start seeing a steady stream of these miracle cures, and then you're going to see a raging river, and then you're going to see a day where cancer falls to gene technologies, and radiation and chemo go the way of bloodletting and leeches, just like I promised you. I know it because of our own research. Here's an example of a mouse where we did what's called a xenograft cancer model. So we put cancer on this mouse's back, so he's carrying this cancer around on his back, but it's not in his liver, so he's not actually suffering from this cancer. Although you can see he's suffering from malnutrition because that cancer is taking so much of the energy from his body to grow. That cancer is growing, and that's actually a human hepatocellular carcinoma that's growing on his back. It's not even a mouse cancer, it's a human cancer. Well, when we treat those mice, the outcome is totally different. An untreated mouse, of course, dies of that cancer eventually, or the cancer gets so big that we have to euthanize the mouse because it's having trouble moving around or it's suffering from malnutrition. But in the treated mice, you see a total difference. And that's an old version of our drug. Our drug now is much, much better. And we're developing that with the help of Dean Felsher, who is a professor at Stanford. So Here is something that may be of interest to you, is that I'm not the only one who's caught on to the future of this market. In fact, Wall Street and pharma companies have caught on as well. Wall Street, it has awarded huge values to a whole handful or a whole bunch of companies, dozens of companies, that actually have no products and no revenue. What does that sound like? It sounds like the dot-com boom. Remember that? The initial internet boom? But the difference here is that all of these companies do have something. They have drugs that have shown some level of efficacy in the clinic, and they're all actually debugging and optimizing these drugs, and I think that they all have hope to bring out new drugs in different disease areas. And most of these companies are working in totally different areas. There's a lot of different diseases that need new cures, and so there's plenty of these different diseases to go around. So in fact, it's possible that every single company on this list could be successful. It could be successful because if it manages to finish that drug and get it working, well, then there's customers for that drug. It's not like the dot-com bubble where, you know, everybody who had an idea could get money from a VC and start a dot-com company, and the VCs would, you know, give you some rationale by which the number of eyeballs helped you to value the company, and as a result, even though they didn't have a way to get revenue now, eventually they'd have a way to get revenue, and those companies went public, and then at some point there wasn't enough revenue to support all those different companies. Well, it's different if each one of these companies that's on this list right now develops a drug that cures a disease. Well, it's going to support the kind of valuations you're seeing right now, and those valuations are in excess of $1 billion in a lot of cases. So these are you know, billion, 2 billion, 3 billion, in some cases $4 billion market cap companies that have no revenue. But I believe that most of these companies will actually have revenue that will backfill these valuations and in fact push them higher. I think that a lot of pharma companies also believe the same thing. So it's not just Wall Street, and a lot of pharma companies are starting to make strategic deals with people that they, or let's say companies that they see as being as having potential in this new market. So there's a number of large companies that have made large investments in this area and large partnership deals, and you can expect to see more of those. So anyway, that's my talk. It's a little bit longer than my original HIMSS talk. I was able to throw in additional topics because I wasn't constrained to the time slot at the HIMSS conference this time. If you managed to sit through this whole thing, I congratulate you. And I certainly appreciate any of the time that you did spend watching this. And I hope you found it informative. And I look forward to living through this revolution with you and achieving all those benefits and seeing all these great things that I am absolutely confident are coming. Thank you.